Hi, this is Mary Sindhuja, working as an associate professor in the Department of Electronics and Communication Engineering at Kamraj College of Engineering and Technology. In this lecture, I am going to discuss about closed loop configuration of operational amplifier. This is the outline of my presentation. So, in the open loop configuration, the gain is not constant, it is varying due to the power supply variations as well as due to the temperature variations. The bandwidth is also very low, so that it cannot be used for linear as well as non-linear applications. So, open loop configuration, we are going for closed loop configuration of operational amplifier. What is closed loop configuration? If a part of output of the operation, closed loop configuration, a part of output from the operational amplifier, it is fed as input so that it can be used for both linear as well as non-linear applications. So, if the feedback is around 180 degree out of phase with the input, then the feedback is called as negative feedback. If the feedback is 0 degree in phase with the input, then the feedback is referred to positive feedback. So, in the closed loop configuration, we are going to discuss about inverting operational amplifier as well as non-inverting operational amplifier. Next, I am going to discuss about inverting operational amplifier. So, in the inverting operational amplifier, the input is given to the inverting terminal of the operational amplifier, so that the output will be the inverted of the input voltage we are giving to the operational amplifier. So, we can say before entering into the inverting operational amplifier, we should know about virtual ground concept. So, according to the virtual ground concept, a high gain is required. So, we can calculate by using V0 divided by Vd. This Vd is the differential input given at the terminal 1 as well as terminal 2. So, we can write the Vd is the potential difference between voltage at inverting as well as voltage at non-inverting terminal. So, in order to make the high gain, the Vd need to be equal to 0. So, when the V1 is equal to V2, Vd will remain 0. So, we can write the gain A is equal to V0 divided by 0, where the gain will become infinite. So, from this we can infer that when the potential at inverting as well as non-inverting terminals are same, high gain can be maintained. So, at the inverting as well as non-inverting terminal, because of the virtual short, there is no physical connection between the two terminals, but due to the virtual short, same potential is maintained at the inverting input as well as ground. So, here according to the virtual ground concept, we can say the Vb is in ground potential. So, this will be equal to Va. Since it is in ground potential, this will be equal to 0. So, we can write the equation as the current entering the node is equal to current leaving the node. So, you can write the first equation, I is equal to V in minus Va divided by R1, input resistance R1. This is the first equation. Second equation, I is equal to Va minus V0 divided by the feedback resistance Rf. So, Va minus V0 divided by the feedback resistance Rf as the second equation. So, according to the virtual ground concept, so we are going to apply this in equation number 1 and 2. So, the equation 1 and 2 becomes, first equation I is equal to V in divided by R1 as Va is equal to 0, and second equation I is equal to minus V0 divided by Rf. Since their left hand sides are same, their right hand sides can be equated. So, we can write V in divided by R1 is equal to minus V0 divided by Rf. So, we can rewrite this equation as V0 divided by V in is equal to minus Rf divided by R1, which is nothing but it is the gain of the inverting operational amplifier. From this equation, several inferences can be done. First inference is, since this negative sign indicates the inverted output of the operational amplifier. So this shows there is an 180-degree phase shift at the output of the operational amplifier with respect to the input. Second inference is the gain of the operational amplifier depends upon the feedback resistance as well as the input resistance. This is the second inference. Third inference is when we consider that RF value is greater than R1, our gain will also be greater than 1. When the RF is less than R1, our gain will be less than 1. And the third condition, when RF is equal to R1, our gain A will be equal to 1. So other inferences from this equations are the gain A is equal to minus RF divided by R1. So when RF is equal to R1, we can write it as A is equal to minus 1. So V naught is equal to minus V in. So at this condition, the operational amplifier will act as an inverter, or we can say it as sign changer. Another condition, when V naught divided by V in, which is equal to minus RF divided by R1. So we can replace for RF divided by R1 by using a scale factor K. So we can write V naught divided by V in is equal to minus K. So this K represents the operational amplifier can act as an scale changer. Next we will see about non-inverting operational amplifier. So when the input is given to the non-inverting terminal of the operational amplifier, it is called as non-inverting operational amplifier. So here, according to the virtual ground concept, the potential at VA as well as VB need to be same in order to achieve more gain. So we can write VA which is equal to VB, but at VB the input will be V in. So we can say VA is equal to VB which is equal to V in. So we will write the equation, current entering the node is equal to current leaving the node. The current flow through the resistor, feedback resistor RF is due to the output voltage V naught. So we can write I is equal to V naught minus VA divided by RF. This is as first equation. Second, I is equal to VA minus 0 divided by R1. This is the second equation. So according to the virtual ground concept, we can rewrite the first equation. I is equal to V naught minus V in divided by RF. Second equation, I is equal to V in divided by R1. So since their left hand sides are same, right hand sides can be equated. So V naught minus V in by RF is equal to V in divided by R1. So V naught by RF is equal to V in by R1. So we are bringing this to the right hand side, so it will become plus V in divided by RF. So from this, take V in as common, so you can write it as 1 by R1 plus 1 by RF. So the equation can be written as V naught divided by RF is equal to V in RF plus R1 divided by RF into R1. So we can write V naught divided by V in, which is the gain, which is equal to RF plus R1 divided by RF into R1. So RF will get cancelled. So you can write it as 1 plus RF divided by R1. So left hand side you can say gain AV is equal to V naught divided by V in, which is equal to 1 plus RF by R1. So this is the gain of the non-inverting operational amplifier. So the inference from this is the gain depends upon the input resistance R1 as well as the feedback resistance RF. Second inference is, since it is a non-inverting operational amplifier, whatever input given to the non-inverting terminal of the operational amplifier, output will have a 0-degree phase shift. And third inference is, when the RF value is greater than R1 or RF value is less than R1 or RF value is equal to R1, the gain will be always greater than 1. Next we will see about voltage follower. So we can explain this voltage follower by considering the non-inverting operational amplifier configuration. So in the non-inverting operational amplifier, when we are considering this RF as well as R1 is equal to 0, we will get this circuit which is a voltage follower. So in the voltage follower circuit, whatever input is given, we will get at the output of the operational amplifier. So we can say that the output always follows the input. So we are calling it as voltage follower. So when the input voltage is 2 volt, at the output also we will get the same 2 volt. So we can say the non-inverting operational amplifier gain AV is equal to 1 plus RF divided by R1. So we have made RF as well as R1 equal to 0. So the gain will be equal to 1 for an voltage follower. So since the gain is equal to 1, we can call it as unity gain amplifier, or we can call it as source follower, and also we can call it as buffer amplifier, or we can call it as isolation amplifier. The advantages of voltage follower, since it is the requirement of the operational amplifier is it should provide very high input impedance and low output impedance. So the voltage follower is connected between high impedance source as well as low impedance load as a buffer. And second advantage is it provides larger bandwidth. Thank you. In the next video, we will see about the simulation of inverting as well as non-inverting operational amplifier using PSIM. Have a nice day.